So, all right, on to example 3. We wanted to solve the triangle once again. We have our side length A is equal to 3, our side length B is equal to 2, and our angle capital A is equal to 50 degrees. So the values we're looking for in this case is going to be lowercase c, angle capital C, and angle capital B. So we want to go ahead and use our law of sines here in order to find, first we're going to go with our angle capital B. So we're just going to dive right in. We're going to pick something and we're going to say, okay, we're going to solve that. So we're going to solve for our angle capital B. So to start, you just want to pick a missing value. We can easily find using our known values. So we know lowercase a, we know uppercase a, we know lowercase b. So since we already know lowercase b, we can easily find uppercase b, which would then lead us to finding uppercase c, which then allows us to find our side length lowercase c. So we're going to use the law of sines to solve for capital B. We know that sine of capital A divided by A, or lowercase a, is equal to sine of capital B divided by lowercase b, so let's just go ahead and use that. So we get that sine of A, which is 50 degrees, divided by A, which is 3, is going to be equal to sine of capital B divided by lowercase b, which is 2. And now we just want to solve. So if we solve for sine of b, in this case, we'll just solve for sine of b first. Sine of b is going to be equal to 2 times sine of 50 degrees divided by 3. But of course, we know that we want to solve for b and not sine of b. So then to solve for actually b is going to be equal to sine inverse of 2 sine times 50 degrees divided by 3. Which now we really want to plug this into a calculator. And when we plug it into a calculator, this ends up giving us the angle measurement of 30.7 degrees. So if B is going to be about 30.7 degrees, we want to check if we're going to have two triangles. So we need to check for two triangles. So we're going to let B sub 1 equal 30.7 degrees, then B sub 2 is going to be 180 degrees minus 30.7 degrees. And what we get here with our answer is we get that B sub 2, this theoretical angle of a second triangle, is going to be 149.3 degrees. So this theoretical second triangle, B sub 2, is 149.3 degrees. And what we see here is that the angle B sub 2 must be discarded. Whatever word you want to think of this, discarded, ignored, removed, anything like that. It's just going to be discarded because the sum of the angles must equal 180 degrees, and A plus B sub 2 is equal to 50 degrees plus 149.3 degrees, which is then equal to 199.3 degrees, which we obviously see is greater than 180 degrees. This means that there's no room left over for any missing angles, which we know can't be true because there has to be 3 angles since it's a triangle. So that's how we can determine that our other angle B has to be removed. So B sub 2 is not going to be used. So we'll only use our angle B sub 1, which was equal to 30.7 degrees, which means we just have one triangle. We can also actually just determine that we were only going to have one triangle anyway, because since we already knew the angle measurement of capital A, and since we know that capital A corresponds to the side length lowercase a, which we can write right here, A, and then length B was 2, and we see that A was greater than B, which means that it's just one triangle. So this was another easier way that we could have solved for this, but using our law of sines would also lead us to this case if we just always checked for the possibility of having two triangles. So you can just put in a note here. We can also determine this since A was greater than or equal to B. Well, moving forward, so we do have our value of B1, which is now just going to be B. So B1 is equal to B, which is 30.7 degrees. And we can find capital C from, once again, using our formula that A plus B plus C is equal to 180 degrees, where A is 50 degrees, B was 30.7 degrees, plus C is equal to 180 degrees. So this gives us 80.7 degrees plus C is equal to 180 degrees. So C is equal to 99.3 degrees. So we solve for C. So now the only length or the only value that we don't have now is lowercase c. So we're going to say lastly, to find lowercase c, we will use the law of sines. So once again, using the angle measurement and side length of capital A and lowercase a, because those are whole values, we're going to set this equal to our sine of capital C over C. So we get sine of 50 degrees divided by 3 is going to be equal to sine of 99.3 degrees divided by lowercase c. Now we don't normally want to use decimals in this way since it does lead us to potentially having an incorrect answer, but since we found the angle measurement of C and it just so happened to be a decimal, this is the only way that we're going to actually find our length of C. So we're going to use it this way. So we have our problem set up here. When we solve for C itself, we're going to get the equation C is equal to 3 sine of 99.3 divided by sine of 50 degrees. And then if we go ahead and we plug this into a calculator, this is going to give us a value of 3.87. So this means that we found the value, so we wanted to, we can say thus, our length of C is equal to about 3.87, capital angle B is 30.7 degrees, and our angle measurement C was 99.3 degrees. All right. So let's just make another note here to kind of drive this idea home. So it's going to be a note based on what we determined here. So we're going to draw a note here. So we have our note. So we're going to say that if A plus B, either B sub 1 or B sub 2, or sorry, if A plus B sub 1 and A plus B sub 2 are both less than 180 degrees. So if whatever you found for the values of B1 and B2, if you add those values to A and they're both going to be less than 180 degrees, then there would be two triangles. Then, if there were two triangles, when solving for your length of lowercase c, using the different angles, or using the different angle measurements of capital C, would have given you two different values of lowercase c. And this is because he would have been separated into two separate triangles, which would then give you two different values of your lowercase c, since you then had two different triangles anyways. In the case of our problem, we didn't have this because our angle measurement of b sub 2 would have made this greater than 180, so we didn't have to deal with it. But if we did, this is how we would go ahead and use it. For the case of one triangle, if you determine that what you're working with is just one triangle, this last step of solving for lowercase c using the law of sines isn't technically necessary. You could use a Pythagorean theorem to solve for lowercase c if you know for a fact it is one triangle. If it's two triangles, you will have to use the law of sines in both cases, because if you just used the Pythagorean theorem to find that length of c, it would give you the entire length and it wouldn't separate it into two separate triangles. This is why we want to use the law of sines as much as possible in order to find this value. But if you know for a fact that it is just one triangle, you can use the Pythagorean theorem to solve for that last side value of c. But if you're unsure in any way and it might be two triangles, you can just use this way. If it is just one triangle, then you would end up with the same value, but at that point it would be very obvious if it was one triangle or two, based on whether or not you had two different values of b sub 1 and b sub 2, therefore, which would then end up giving you different values of your capital C. So, all right, just a quick note of that. If you do want to look at more examples of the different cases you would then have for seeing if you have one triangle, two triangles, or no triangle at all, please go into the book. You can look through the different types of examples. For time's sake, we're just going over this one and then one more in our applied problems. But if you do want to look at more examples, by all means, you can go through the book. They have an example of every single type that you could go through. So, all right, here. Moving on to our last objective, objective 3, we want to solve some applied problems. So example 4, to measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. See figure 31A, so these are figures 31A and B. on the next page, which this was technically on the next page, but now it's not. The first observation results in an angle of elevation of 47 degrees, and the second results in an angle of elevation of 35 degrees. If the transit is 2 meters high, what is the height h of the mountain? So in figure 31a, we see, this is the illustrated image here. We have our person and they've moved a certain length apart and they're looking up at the mountain using our angle of elevation here. We see we have there are two different angles for one person who is looking farther back and one person who is looking closer to the mountain. Then for figure 31b, we really just have the drawn out version of what's happening in our illustrated version. So it gives us a little bit of a clearer image for figure 31b on what kind of really is happening here. And our final answer here that we want to find is we want to find the height of the mountain. This is what we're going to be looking for. And this is already given to us in our problem, but we obviously have two triangles. And since we have two triangles, means that we're going to end up with some different values of C. So our angle measurement C. So we will have to use those values. So all right, let's get started. So for our first triangle, so for this triangle here, and let's make that a different color. For this triangle here, we'll just call it 1, and this will be triangle 2. So from triangle 1, we can say that C plus 47 degrees is equal to 180 degrees. So capital C is equal to 133 degrees. And this is just from triangle 1 here. Then also in triangle 2, we see we have a degree measurement of A, we get that A plus C plus 35 degrees is going to be equal to 180 degrees. Which then we can say that A is going to be equal to 180 degrees minus 35 degrees minus C, which we have our angle measurement of C from, which is 133 degrees. We got our value of 133 degrees. This is because our half angle measurement here is 180 degrees, and we've already portioned off 47 degrees of that. So our angle C, which is in technically triangle 2, we found the value from adding the values from triangle 1 and triangle 2 to find the value of capital C for triangle 2. That's how we got our value of 133 degrees. So our value of A, which is now 180 degrees minus 35 degrees, which gives us 145 degrees, minus 133 degrees, which is C, gives us a value of 12 degrees. So A is 12 degrees, or our angle measurement A. Our angle measurement A is 12 degrees. And what we want to do is we want to find the value of lowercase c in this case. So we can use the law of sines to find lowercase c. So we have sine of A, which is 12 degrees, divided by our value of A, which is 900 meters, because remember, our angle A corresponds to this side here, which is 900 meters. So sine of 12 degrees divided by 900 meters is equal to sine of C, which is 133 degrees, divided by lowercase c. Then, of course, once again, solving for c, we end up getting that c is equal to 900 times sine of 12 degrees divided by sine of 133 degrees. Ooh, I apologize. Those are flipped. Sine of 133 degrees divided by sine of 12 degrees. I apologize for that. And when we plug this into a calculator, we end up getting the value 3,165.86. And this is in meters. So this is our value of lowercase c. So lowercase c is this incredibly high value. Then we're going to say that using the larger right triangle, so using triangle 1, which we labeled, which is our larger right triangle there. So using triangle 1, we can find the value of, in this case, B. We see that B is just 2 meters shy of the actual given height. So when we find the value of B, we can just add 2 meters to find the height. But using triangle 1, we can find the value of B just using our formula for sine of theta is equal to opposite over hypotenuse. Since we have sine of, let's draw the blue here, sine of 35 degrees corresponds to B over C, which we've now found the value of lowercase c. We're using this angle here. So we're going to state that sine of 35 degrees is going to be equal to B over C, or B over 3,165.86. Which then, if we just go ahead and we solve for B, B is going to be equal to 3,165.86 times sine of 35 degrees. So once again, we're going to have to put that value into a calculator. And when we do, this tells us that B is going to be about 1,815.86, which a part of our problem here, we're just using approximate values since these are applied problems. So we're going to round up to the nearest whole number, which gives us 1,816 meters. So this is our value of B, and we know that our height, we say the height of the peak from ground level is approximately 2 meters more than the length of B. So we get that h is equal to 1,816 plus 2, which gives us 1,818 meters. And this there will be our final answer. So when using applied problems or solving for applied problems, it's really just going to be, what can I solve for first? What can I solve for next using what I have given to me? And then how am I going to take all this information and find what I'm actually looking for in this question? So it's really just going about different ways in solving for certain and specific values so you can solve for the final value that you want. There would be different ways that you could go about solving for this problem, and you would be able to find your final value of your height h. This is just one of the most straightforward ways that you could go about this for this specific problem, but there are different ways that you could do this if you choose to do so. If you would like to see other different applied problems, there are many in your book as well that you can go ahead and look through, which I highly suggest doing that as well. So you get a feel of more of the applied problems for our sections as well. So all right, that wraps up section 8.2, and I'll see you again in section 8.3.